Hello, welcome to this video 6-6, and in this video we are going to talk about calculating volumes of solids by rotating objects. Okay, this is an application based upon 6-5 where we calculated volume with cross sections, and we'll start with our knowledge from there. So here is our first example, and it's kind of like a warm-up example, taking your knowledge again from 6-5. So it says, if for a given base you create a semicircular cross-section, one sticking towards you and then also one sticking away from you, that would actually be a circular cross-section. And since the formula for the area of a circle is pi r squared, the volume for a circular cross-section is the integral from a to b of pi r squared, right? That's your cross-section as a circle, times dx, which is your width. Now, if we're integrating perpendicular to the y-axis, it would be with dy, but most of the examples will be with the x-axis, and you might have some with the y-axis. Okay, so let's go ahead and utilize our knowledge of cross-sections to find the region bounded by y equals x squared and y equals negative x squared, x equals 0 and x equals 1, as shown, to create the volume by using a circular cross-section perpendicular to the x-axis. So when they want volume, well, volume is equal to the integral from our bounds. So we know our bounds are 0 to 1. And I know I have a circular cross-section. So the formula for a circular cross-section is pi r squared. And when they say perpendicular to the x-axis, that tells me it's dx. So I just have to ask myself, okay, if this is my circular cross-section right here, what is the radius of that circle? And that would be just half of it, right? From the x-axis up here, right? And that distance would just be y equals x squared. Okay, so I can go ahead and adjust this. This is going to be the integral from 0 to 1 of pi times x squared, quantity squared, dx. And if you want to, especially when we start calculating, you might want to pull out the constants. So you would have this, okay? All right, so this is similar to what we're doing today. Circular cross-sections can also be formed by revolving very thin, essentially no width rectangles about an axis of revolution. These circular cross-sections are more commonly called discs, and hence that this lesson is on discs. A volume formed by revolving a region about a line that does not pass through the interior region is called a solid of revolution. The line is called the axis of revolution. And most of the time, the x-axis will serve as your axis of revolution, or the y-axis if we're integrating with respect to y. But sometimes that might change, and we'll look at some examples. If a region is bounded by the axis of revolution, then the volume of the solid of the revolution is the sum of all the volumes of essentially an infinite number of cylindrical discs. So the same idea. And in example 1, you're looking at the same type of volume in our warm-up example. Here I just have the line y equals x squared. And what we want to do is set up an integral for the volume of the solid formed by revolving the region bounded by y equals x squared, y equals 0, which is your axis of revolution, and x equals 1. Okay, so what you can imagine is you can take this slice, right, and I'm going to rotate it around this line. Okay, and what ends up happening is you get a three-dimensional object that looks a lot like this. Okay, so we're calculating that volume. All right, so I'm going to go ahead. I'm going to set up my integral. So volume is equal to the integral from 0 to 1. Okay, and when I'm rotating this, my base is going to be a circle, okay, and that is pi r squared, okay, dx. So again, what's our radius? Well, our radius is equal to x squared, so 0 to 1 of pi r squared, which is x squared dx. And there is your answer. Okay, so there is our integral. All right, example 2. they want us to go ahead and find the volume of a solid formed by revolving the region in quadrant 1 bounded by y equals x squared, x equals 0, and y equals 4 about the y-axis. So notice this time we are rotating about the y-axis. So here's our line, okay, and we're going to spin it this way, right? So our function will look something like this. Okay, so there's our solid, and we're rotating this way. So I know that this integral is going to be with respect to y. Okay, so my cross section or my rotation is still a disk. So that formula is going to be pi r squared. Okay, dy, and since I am rotating about the y-axis, my bounds need to be in terms of y. So notice here that they say y equals x squared, x equals 0, which is this line here, okay, and y equals 4. So I have my bounds here, okay, so my bounds for my integral will be 0 to 4. And I just need to go ahead and now plug in the radius for this cylindrical circle. Well, again, the distance from here to here is x. So I'm going to take my function y equals x squared, and I'm going to solve for x. So x is equal to square root of y, okay? So I'm going to plug in. Do I plug in x or y? Well, we're going to plug in whatever our function is in terms of y, because we're integrating with respect to y. So I'll simplify this. So 0 to 4, I'll pull out the constant, and I have y dy, which is equal to pi times y squared over 2. Evaluated from 0 to 4. Okay, and if I plug in 4 squared, that's 16 divided by 2 is 8. So this is 8 pi minus 0. Okay, and that would be your answer, or 8 pi. All right, that's it for the disk method. I'll catch you next time. Peace.